Ever get stuck with that spinning wheel of doom because your Wi-Fi is moving slower than molasses?
Ugh, tell me about it. It's like the internet just goes on vacation when you need it most.
Today's deep dive is going to make you appreciate just how much engineering wizardry goes into making sure that doesn't happen, even when everyone and their cat is online at the same time.
This sounds complicated.
Buckle up, because we're talking MIMO, that's multiple input, multiple output.
Okay, already lose me.
Don't worry, it's not as scary as it sounds. It's actually pretty cool once you get the hang of it. And we're going even deeper with a technique that's basically like bending the laws of physics. Interference alignment.
Ooh, now that's got my attention. Interference is the bane of my existence.
Right. It's like everyone trying to squeeze through a doorway at the same time.
Exactly. And that's a great way to think about it, actually. The wireless channel, it's like that doorway. Signals trying to get through at once, total chaos. Your connection slows to a crawl, things get spotty.
Speaking of chaos, we've got some excerpts to guide us through all of this. And to keep us on track, I've got our expert here with me.
Happy to be here. Always happy to talk about how signals actually work.
All right, so first things first, interference. We all experience it. But why is it such a pain in the neck for wireless signals?
Well, you pretty much nailed it. Too many signals in the same space. It's like your source material says on slide 2, think of everyone shouting into their phones in a crowded room.
Okay, I can picture that.
Right. That's essentially what happens in what we call the interference channel.
Ouch, my ears are hurting just thinking about it. The source material also throws out this equation. What's that all about?
Okay, so in that crowded room, imagine you're trying to have a conversation, right?
Good luck with that.
That conversation you're trying to have, that's your why of what you actually want to hear.
Makes sense.
But then you've got someone blasting music next to you. That's your X1 meter. And another group chatting loudly nearby. There's your X2M.
Plus a million other conversations happening all around.
Precisely. And then there's just the general murmur of the crowd, clinking glasses, that's your W, the unavoidable background noise. So the whole equation, it just shows how all those signals combine into this big mess that the receiver has to deal with.
Okay, so it's basically a recipe for a jumbled mess of sound. No wonder our devices struggle sometimes.
Right. It's a wonder we can send any information reliably with all that noise.
That was my next question. Seriously, how do we even begin to send data reliably with all that interference?
Well, that's where this idea of channel capacity comes in. It's the maximum rate, think speed limit, for data at which we can send data over a channel and still have it be understandable on the other end.
So more interference means a lower speed limit to avoid those data accidents.
You got it. And that's the challenge, a bunch of senders all competing for the same limited space in that wireless channel.
So what do we do? Like with the crowded room just shouting louder, or in our case, increasing signal power that doesn't really help, does it?
Nope. Just makes everyone else crank up their volume too, and then it's even worse.
Right, a total mess.
Yeah.
So how do you fix this? How do we make that doorway wider, so to speak?
That, my friend, is where MIMO swoops in to save the day.
MIMO. You mean like multiple something something?
Multiple input, multiple output. Instead of one lonely antenna trying to handle all that traffic, we have multiple antennas, like a whole team of them, at both the transmitter and the receiver.
Oh, I see. So instead of one tiny door, it's like we've suddenly got a whole row of them.
Exactly. We call that spatial multiplexing. It's like adding extra lanes on a highway, so we can transmit multiple data streams at the same time.
Okay, so multiple lanes, that makes sense. But even with multiple lanes, don't we still need some way to direct all that data traffic?
You're way ahead of me. That's where things get even more interesting. One approach is called zero-forcing MIMO. Basically, we try to isolate each signal by blocking out the interference from other antennas.
Clever. So like noise-canceling headphones, but for wireless signals.
Exactly. Effective, but it turns out it's not the most efficient technique.
There's always a cooler, more efficient way, right?
Yeah.
Something tells me this is where those eigenmodes come into play.
You're catching on fast. And this is where understanding how signals naturally behave in space gets really wild. So, eigenmodes, they get a bad rap, sound way more intimidating than they actually are.
Okay, I'm listening. Convince me. Because the word just makes me think of something out of Star Trek. Like, are we about to beam data across the galaxy or what?
Not quite intergalactic travel, not yet, anyway. But they are pretty cool. It's all about how signals, any signals really, naturally behave as they travel through space.
Okay.
Like, imagine a sound wave just traveling through a room. You ever notice how there are those certain spots where the sound seems louder or clearer?
Yeah, like it's hitting that sweet spot where the wave resonates or something.
Bingo! Those sweet spots, those are like eigenmodes in a wireless channel. They're like special directions where signals can travel with way less interference.
So you're saying there are these clear lanes for data
Hmm.
hidden within all the chaos of the wireless channel.
You got it, like finding those secret shortcuts in a maze, you know?
Okay, I'm with you so far. But how in the world do we actually find these eigenmodes? This is where I always get lost.
So luckily, we have a secret weapon, singular value decomposition.
SVD. Come on, you're not making it any easier.
It sounds worse than it is promise. Okay, new analogy time. Imagine a jumbled Rubik's Cube. You know how annoying those are to solve.
The worst.
Well, SVD is like having that set of instructions that tells you exactly how to twist and turn that cube to get all the colors lined up perfectly.
Okay, so we're talking about bringing order to the chaos.
Precisely. In the context of MIMO, SVD basically helps us figure out those eigenmodes, those optimal directions that give us the least amount of interference for our data.
So it's like SVD is giving us a map of the best routes through the wireless maze. Pretty cool.
Exactly.
Nice. Okay, so say we've found these eigenmodes. What do we actually DO of them?
Okay, this is the really cool part. We use a technique called pre-coding.
Pre-coding. Sounds intense.
Basically, at the transmitter, before we even send anything, we pre-process the data and like aim it along those clear eigenmode directions.
So we're carefully aiming our data for the best possible reception, kind of like lining up a shot in billiards.
Exactly. And then at the other end, the receiver does something called post-coding to make sure those signals all get captured without getting jumbled up again.
Nice. So pre-coding plus post-coding, all thanks to MIMO. That's how we get those crazy fast data rates, right?
You got it.
Wow, who knew there was so much strategy involved in just sending a text message? All this actually reminds me a bit of OFDM, which we've talked about before on the show.
Oh, great connection. They're actually very similar, but in a cool way. Both OFDM and MIMO, they both want to make those independent channels for data, but they do it in totally different ways.
How so?
So OFDM, it's like having different radio stations. Each one's broadcasting on a separate frequency so they don't interfere.
Yeah, that makes sense.
But MIMO is like having a bunch of antennas all talking on the same frequency, but they're talking in different directions so their signals don't crash into each other.
Ah, I see. So it's like we've got all these different tools to combat interference depending on the situation.
Exactly.
But we can't stop there, right? You know how we do on these deep dives? You got to push the limits.
How do you turn noise into like a helpful thing?
All right, so imagine you have a bunch of spotlights all pointing at the same stage, right?
Okay, yeah.
Instead of just letting their beams overlap all over the place, what if you could control them so they all came together at a specific point, minimize the spillover?
So instead of trying to get rid of interference completely, we're talking about like controlling it.
Exactly. IA is about aligning those interfering signals strategically so that receivers can still pull out the data meant for them.
Okay.
Example, with two clients trying to send data to two access points, like a tiny network, just to illustrate.
Okay, walk me through this two-client thing. What's so special about that scenario?
So each client wants to send a data packet to both of the access points.
Right.
Without IA, these packets would just crash into each other and interfere. Total mess at the access points.
Sounds like my inbox. How does IA fix that?
Pre-coding. Before sending its packets, each client pre-codes its signal.
Like adding a code or something.
Basically, think of it like a unique key that unlocks the message. This pre-coding ensures that when the signals combine at the access point, they combine in a way that makes them easier to separate later on.
So each packet has a specific key to unlock it, even in all that mess.
Precisely. Now here's the really clever part. The two access points have this wired link between them called a backhaul.
Okay.
Access point 1 decodes one data packet from each client because of how the interference is set up, and then sends one of them over to access point 2 through the backhaul.
So they were sharing the load.
Exactly. So now access point 2 has one packet from each client, one it got directly, and one through the backhaul. Remember that pre-coding?
Yeah.
This lets access point 2 basically subtract the packet it knows from the combined signal, leaving just the other client's data, which it can then decode.
It's like they planned out this whole intricate dance, and each access point knows exactly where to be to get the data to the right place.
It's a beautiful thing. And while this example is simplified, it shows how IA could change how wireless networks work. Imagine scaling that up to a network with tons of devices all coordinating. That's the future IA promises.
Sounds awesome. But what are the downsides? It can't be this easy, can it? There's always a catch. What's the catch with interference alignment?
The number of antennas is really important.
Okay, so more antennas, more data we can send without things getting jumbled up.
Yeah.
Makes sense.
Yeah, to a point. See, in that two-client example, it's like we were working in a two-dimensional space, like a graph, right?
Right.
Each antenna adds another dimension,
Right.
like going from a flat graph to a 3D one, adding that z-axis. With more antennas, we can align more signals without them crashing into each other.
So more antennas, more room to maneuver, more space for that data dance.
Exactly. But here's the thing. Even with a ton of antennas, there's only so many signals we can perfectly align.
So eventually our dance floor is just too crowded, even with all the fancy footwork.
You got it. Plus, it gets complicated. All that pre-coding, all that coordination between the access points, that takes a lot of computing power and a lot of back and forth.
So we're gaining speed, gaining efficiency, but it's getting more complex.
Right, which is why, for now at least, IA works best in places where you have more control, like company networks or data centers where you can handle that complexity.
So not for my home Wi-Fi anytime soon.
Probably not. We've been talking about the uplink, right? Data going from our devices up to the network. What of the downlink? Data coming from the network to us.
Oh, that's a good point. Does IA work the same way in the downlink?
It does. The access points can coordinate, pre-code their signals before sending them to our devices.
But hold on, the access points can talk to each other with that backhaul connection. Our phones and laptops and stuff, they can't really do that, can they?
Good point. For the downlink, the access points would need to figure out their strategy ahead of time, like planning out that dance before the music starts.
So they're choreographing everything in advance so that our downloads are smooth.
Exactly. It all comes down to working together.
Mm.
When these networks share information, coordinate, they could do some amazing things.
Well, we went from crowded cafes to choreographed data dances today. The future of wireless communications sounds pretty awesome.
And we're just getting started. If we can use interference, something we thought was just a pain, and make things better, what other challenges can we solve? What other limitations can we break through?
That's something to think about. With a little creativity and a lot of collaboration, seems like we can turn any limitation into an opportunity. Who knows what the future holds for wireless communication, but it's going to be exciting.